Okay, today's class is about Newton-Raphson method. This is a very important method for solving the transcendental equations, transcendental linear equations. This method is very powerful method for solving different types of square root, cube roots and everything. Now, what is the Newton-Raphson iteration method is? Suppose we want to find an approximate solution to the equation fx is equal to 0. To see how the method works, we will sketch first. We have to sketch the y is equal to fx using, suppose we assume here the fx is x cube minus x minus 1, and the plot shows that here the curve y is equal to fx cuts the x-axis at the range, between the range from 1 to 2, and the root alpha. Suppose the root of this equation is alpha, that means that cutting point lies between 1 and 2, and we will zoom near alpha. Here the picture shows, the zoom picture, that the alpha belongs to, between the alpha belongs to, lies between, that means alpha lies between 1 and 2, and the range of this above equations, the range of the root of this above equation is 1 and 2. Now what happened? Suppose our first estimate is given by x naught is equal to 2. Here from the y-axis and x-axis diagram, we draw the tangent to the curve at x is equal to 0, and this tangent, we are noticing that it cuts the x-axis at point x1. Now repeating this, again we draw the tangent at the point x1, and that tangent also cut the x-axis at point x2. So each point x1, x2 dot 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 is a closer to the alpha, and alpha is a actual root which is lies between 1 to 2. And now to carry out the iterations, we need to find the points where the tangents meet the x-axis. That means if all the tangents drawn like this way will cut the x-axis at the different points, and all the points are the roots, the approximate roots between the 1 and 2 ranges, and that roots are closer to the alpha. Alpha is the actual root. Now this is some deductions shown here. The gradient of the tangent at x is equal to 0 is the change in y by the change in x. So what happened? The distance along y-axis is y0, and the distance of the along x-axis is x0 minus x1. So the dy dx, by definition at x0, what will be the value? Now x0 is equal to y0 divided by x0 minus x1. We have dy dx at x0 is equal to y0 divided by x0 minus x1, and we need to find another point, another approximated point, that is another root, assume root x1, where that second tangent cuts the x-axis. So from the equations we can use, here we may use y is equal to fx. So at the point x0 we can write y0 is equal to fx0, and at dy dx, and the value of dy dx at x is equal to 0 is y0 divided by x0 minus x1. So it is called the f dash x0. Then So we can write from here f dash x naught is equal to y naught by x naught minus x1, and we replace the value of y naught, that is from this equation is f x naught by x naught minus x1. So rearranging, x naught minus x1 is equal to fx naught divided by f dash x naught. So it implies from here we can find out the value of x1, that is x naught minus fx naught by f dash x naught. So x1 is equal to x naught minus fx naught divided by f dash x naught, right? We just need to alter the subscripts to find x2, and iteratively we approaches and find out the value x2, x3 and dot dot xn and xn plus 1. So ultimate generalizing the equations, it comes xn plus 1 is equal to xn minus fxn divided by f dash xn. So it converges very fast. The Newton-Raphson method converges very fastly. Here some examples. Suppose at x is equal to, use the Newton-Raphson method with x naught is equal to 2. Suppose this is the approximated root, initial root. Find the actual root of these equations, and that should be correct up to 4 decimal point. So here fx is equal to this, considering this. So f dash is equal to derivative of this. So using this formula, students who wants to use the calculator, so they can use xn plus 1 is equal to xn minus xn cube minus xn minus 1 by 3xn square minus 1. That in the calculator as the input they can take the 2, enter, then answer minus this formula, answer minus these total terms they can use, and easily they can get the values of the above equations, that is root of the above equation is 1.6180. This is up to 4 decimal of the places. Here are the summary of the Newton-Raphson method. What is the summary? To use the Newton-Raphson method to estimate a root of an equation, rearrange the equation into the form fx is equal to 0, differentiate fx to find f dash x, substitute fx and f dash into the proved formula, and choose a suitable starting point value for x naught. That means root belongs to in which domain, you just take the ultimate value, either x naught or either x1. If x naught and x1 is the range, and use calculator to iterate and get the exact value. Here are the examples of the Newton-Raphson methods. The students have to find out the root of these equations up to 6 decimal of places. Here are the others more examples. And now this is the procedures to solving the equations. This is the procedures to solving the root of these equations, and this is like the previous one. And now last of all, Newton's Raphson method is a suitable method for finding out the any square root of any numbers, and the square root of any number. Suppose here the example is the x is equal to root a, and you have to construct the equation fx is equal to x square minus a square. Now using this formula, xk plus 1 is equal to xk minus xk square minus a square by 2xk, and taking a is equal to 5. If a is equal to 5, then these roots will come, and automatically the root of the above equations is found out. And this is the very important methods to find out all the cube root, square root, and every powers of the every powers of the any equations. And it is very important formula. Newton-Raphson method is a very useful formula to find out any cube root, square root, tetra root of any number at any moments. Thank you.